Ok, donc bonjour à toutes et à tous, bienvenue à Paris. Good morning everyone, and welcome to Paris, to this 21st European Radar Conference, EuRAD2024. I'm Guido Valerio, the General Chair of the conference, and I'm here together with the EuRAD2024 team, myself from Sorbonne University here in Paris, Alan Jenkins, the co-chair of the conference from Valeo, Kamela Dadi from IEMN CNRS is the EuRAD TPC chair, Olivier Latry is from GPM Rouen, he's the TPC co-chair, and he apologizes he couldn't be here today because he's organizing the radar school taking place tomorrow and on Friday. I will talk about this a little bit more later. And we also have Guillaume Ducournau, who is the European Microwave Week General Chair here with us. We would also, we will all like to welcome you at this new EuRAD conference. We are 571 delegates and counting. The number is from yesterday evening, but other delegates are joining us today here in Paris. So let me introduce you briefly the content of this next 3 days of EuRAD. We are starting now the opening session, and most importantly, we are going to listen to our two keynote speakers. So Professor Peter Burke from University of California, Irvine, California, US, who is going to present application of microwaves at different scales, from nanoscale to macro scale. So we are going to see nano-radars and drone for long-range radars. And at 9:30, we will have Bjorn Rommen from European Space Agency, who will give us an overview, a status and application of missions ongoing at European Space Agency of synthetic aperture radars. After the opening session, we will have several technical sessions, of course, and I will give you a bit more details during the next minutes. And the conference will end on Friday afternoon with our closing session, where the third keynote speaker of the conference will present, Joachim Mattes of Valeo. He will explain to us why software-defined vehicles is more than a buzzword nowadays. After the keynote speaker, again on Friday, we will have the award ceremony. This will be chaired by the award chair and European Microwave Week TPC co-chair, Olivier Lafont. And we will deliver 3 prizes, one a European Conference Prize, who will be sponsored by Thales Netherlands, and 2 Young Engineering Prizes, sponsored by Hensoldt and Thales Netherlands. Professor Lafont will give us more details about the rules, the selection of the candidates, finalists, and the selection of the winners during the final award ceremony on Friday afternoon, so don't miss it. And at 3 p.m. we will have the closing remarks from myself and Kamel, but most importantly we'll be invited for the next European Radar Conference in 2025 by the EuRAD 2025 General Chair, Laura Nitori, who will join us for this warm invitation. The invited speakers will be completed also by 2 invited industrial keynotes that will present tomorrow afternoon at sessions EuRAD 8 and 9. They are Mathieu Chevrier from Texas Instruments, who will talk about robotic safety enabled by millimeter wave radar, and Florian Baumgarten from Carrier Technology, who will discuss about challenges in radar-based motorbike detections. The technical sessions will add also some short courses and student school. So we have 2 short courses labeled as EuRAD conference. One is tomorrow morning. It's shared with the European Microwave Conference, and it's on basics of system engineering for microwave engineering community. Another short course on Friday will be on radar waveform optimization mastery, and will be Friday afternoon. And we also have a student school on radar. This will be repeated twice with the same content on Thursday and on Friday, the entire day. And as I was saying, is organized by Olivier Latry. Beyond the short courses, we have a few workshops. So one of the workshops took place already on Monday. It was shared with the other 2 conferences on millimeter wave packaging and RFICs for wireless communication and radar sensing.
Other workshops are planned on Thursday afternoon on radar networks.
On Friday, the entire day, on free space radar sensing for electromagnetic materials modeling and characterization. And also on Friday, the entire day, shared with the UMIC conference, chipless RFID systems, future and challenges. So this sums up the activities, the scientific activities that will take place in the next couple of days here in Paris. Let me also remind you a few conference events that we are organizing this week. So if you were here already yesterday, I hope you join us for the welcome reception sponsored by Keysight. It was yesterday at 7 p.m. We had a lot of fun and very good food, I would say. I will remind you that this evening we have the gala dinner on the Seine River, on the typical bateau mouche. So if you book the, I think it's full booked now, but if you book the ticket when you registered, you will receive an email this morning with instructions to join the event directly on the Seine, and the tickets will be distributed at the registration desk later in the morning. These are sponsored by Roden Schwartz. I think it will be a very fine event, a very nice opportunity to spot the Parisian landmarks during night along the River Seine. So I would really advise you to come if you booked your place. On the other hand, if you're a young professional and you're now starting your career, we would also suggest another program. It's taking place today. It's the Career Event Networking. This is going to happen today at the conference here at starting noon. This is sponsored by the IEEE MTTS Young Professional Committee and Diversity and Inclusion Committee. There will be a meeting, a recruiting event for young students, PhD who are there the last years, postdoc who are looking for a job. So there will be an opportunity to have interviews with these companies. You will find also more details on the program. The companies will also deliver tickets for the event of the evening, which is a career party at 7 p.m. organized at the Bois de Vincennes, which is on the east part of Paris. And again, all the details will be given in the ticket and on the conference program. So if you are a young professional looking for a job soon, well, we would advise you to join the party. A few more details. This is for the first time this year. We decided to serve seated lunch every day. So those of you who were here yesterday have already seen there is a space reserved for this at the exhibition center. This will be very easy to spot, and namely on Friday, the EuRAD lunch will be confirmed as last year, and it will be open for all EuRAD delegates and all delegates who have short course and workshops on Friday. And of course, this will take place just shortly before the closing session of EuRAD. Now, a few figures on the conference this year. We received 161 papers. They were divided into different topics. This is what we call subcommittees. Radar subsystems and phenomenology, radar techniques, localization, waveform diversity, joint radar and communication, radar signal and data processing, imaging, ultra-wideband short range, millimeter wave terahertz technologies, quantum radar architectures and radars, high frequency over the horizon radars, passive architectures and systems, and broader committee on radar applications. And you see that every application has the number of submissions. Now, the reviewers, the EuRAD reviewers, worked hard to provide a serious and extensive peer review to all the papers. And so the reviewers and the TPC members of each subcommittees that we really need to thank for their work, for their hard work. It's not an easy task, it's a time-consuming task. Selected 110 papers with an acceptance rate of 68%, which is a typical acceptance rate for the microwave week. So you will see at the conference 90 oral papers and 20 posters. They are arranged in 20 different sessions. Up to 4 sessions in parallel for EuRAD, and we have one joint session with the European Microwave Conference, an oral session, and another one joint session again with UMC. It's a poster session. Now, a few figures about the countries of the accepted papers. The strongest contributed country is, as usual, Germany, followed by Netherlands, France, Great Britain, US, Belgium, and South Korea. So it's just to show you that where the people you will meet in these two or 3 days are coming from, and so how the attendees of the conference are composed. So let me finish this short address by thanking, first of all the authors, all the presenters, all the attendees at the conference, all the proponents of short course and workshops. You really are making the conference. Without you, this wouldn't be possible. And for the organization point of view, of course, we thank the European Microwave Week team of this year, especially the chair of the week, Professor Ducournau, and all the people involved in the team. It's a big event. It cannot be done by 1 or 2 people, so it's really a teamwork, and we were supported by all people in the team. It was really necessary to come here. Thanks you to the EuRAD reviewers, I was saying, TPC members, session chairs. Thank you for your continuous support to the EuRAD conference and the Microwave Week event. That's very precious for us. We really appreciate your time spent volunteering for these tasks. Thank you to the previous European Microwave Week teams for their suggestions last year in Berlin during the year. It was very useful. So we hope we will be as useful for the next team. We'll do our best. And thanks to the European Microwave Week Prize Chair and all the colleagues who accepted to be part of the prize committee. And thanks to our sponsors. I tried to cite them all during my previous slides, but I must have forgot something. And last but not the least, thanks to all the student helpers who are really giving a big help for this organization, for the practical organization of the sessions, because it could be possible to run such a big event without their help. So I think now we are ready for the real talk of the day. So in order to introduce the first keynote speaker, I give the floor to Kamela Dadi, TPC Chair of EuRAD2024, and I will wish you a very pleasant and successful EuRAD conference in the next 3 days. Thank you very much.
Good morning. So this is my pleasure and honor to welcome our first keynote speaker, Professor Peter Burke. So Peter Burke, a Chapel E Fellow, received a PhD degrees in physics from Yale University, USA, in 1998. From 1998 to 2001, he was a Chairman Fairchild postdoctoral scholar in physics with the California Institute of Technology, Caltech. Since 2001, he has been a faculty member with the Department of Electrical Engineering and Computer Science, University of California, Irvine, UCI, and courtesy appointments in biomedical and biomolecular engineering, material science, and physics. His current research interests include nanoelectronics, props of cellular and subcellular electrophysiology, mitochondria, radio and antenna propagation and system, which includes nanoelectromagnetics and drones. Peter Burke has been a recipient of the Office of Naval Research Young Investigator Award and the Army Research Office Young Investigator Program Award. Please, Peter.
Good morning. It's a pleasure to be here to speak this morning. Paris has a special role in microwaves. The Eiffel Tower was built in 1889 by Gustave Eiffel and colleagues, and it was only supposed to be up for 20 years, and then they planned to tear it down. But because of its use in antennas and radio waves, they kept it up, and now it has over 120 antennas on it. Marconi in 1901 demonstrated the first transatlantic telegraph, and the rest, as they say, is history. Now, I really enjoy this community, although I've worked in other fields, and wireless engineering has changed the world. And wireless engineers I see as the Jedi Knights of the world. They're small in number. It takes, unlike a software programmer where you need a laptop and you can learn it at home, it takes years of apprenticeship with hands-on experience. And the impact is disproportionate to the number. So it's a great pleasure to be a part of that community. So the biggest impact is in communications. And the theme of this conference is Waves Connecting Europe. And if you start with Heinrich Hertz's first discovery of electromagnetic waves in 1888, you can look at the implications of that for technology in communications as the biggest impact. So that's led rise to person-to-person communication, smartphone, industries like Google, Facebook, Snapchat, Instagram, WhatsApp. And that's what a lot of this conference is about. But there's frontier research areas in other fields that go to the theme of the conference, which is Waves Connecting Europe, which is not just waves connecting people to people, but waves connecting people to the physical world and the physical world to people. And waves connecting, I would put that in probes where we can use waves to probe the physical world. And radar is the biggest example, which is the theme of this conference. MRI is another example. And one of the frontier areas that I'm going to be talking about in the first half of my talk is using waves to probe at the nanoscale inside of cells. So that's going to be the first half of my talk, is waves probing at the nanoscale, what they can be used for. And that's a research area, an emerging research area. And the other thing that waves can be used for is not just to sense the physical world, but to control the physical world. And this is a much larger research area and newer, and one of the biggest applications is in aviation. And I'm showing here a slide of a drone light show over the Eiffel Tower. Those are kites, and you can see on the top about 1,000 or so drones. And this is going to revolutionize aviation, which I'll talk about in the second half of my talk. And waves are going to be used for control of the physical world, not just sensing it. So you can see my background is in physics, as Camille said, and I like to think we live in a physical world, as Madonna says. So it's very important to understand the laws of physics and how they apply and how they can be used for sensing and controlling with waves. So the first half of my talk, I'll be discussing waves at the nanoscale. And one question I've always posed, and I don't have an answer, is there a Moore's law for radio slide? So yesterday at the opening talks for the European Microwave Week, there was a discussion of Moore's law and shrinking of transistor size. Is there a shrinking of radio size? And can you eventually build a radio that would fit into a single cell? And this is a very different, this could be a very interesting application area, but it's a very different engineering area than most of the conference is used to. Because here the metrics are small size and low power, very small size. Whereas a lot of the metrics that are discussed in this conference and in the microwave engineering community in general are range, bit rate, gain, efficiency, and all of these metrics are demoted. So this gives rise to a different set of design constraints that has yet to be completely developed. And the two key challenges are the antenna and the power. So I'm not going to talk about the power in this talk because of time, but the antenna is something that I've thought a lot about and worked actually with Lille in France on this project, and I'll discuss progress in that direction and future opportunities. So first question is, what is the smallest antenna you can make? Now you can make an electrically small antenna compared to the wavelength, but what happens if you shrink the antenna size down to the atomic dimension? What happens? And the reason I started thinking about this is that one of my students made a very, very long nanotube that's about 1 centimeter long, and she discovered a way to do it. And then we looked at that, and the diameter is 1 nanometer, the length is a centimeter. Now, so can that be an antenna? And it turns out, to my knowledge, and please correct me if I'm wrong, that the only antenna pattern that can be calculated analytically without the computer is a dipole in the Taylor, and you do a Taylor series in D over L, where D is the diameter of the antenna and L is the length. And this is done by Shulkinoff. And as far as I know, all other antenna patterns and radiation characteristics are done computationally. So this is, I think, the closest physical approximation to Shulkinoff's theory that exists in the physical universe. Please correct me if I'm wrong, but the diameter divided by the length is 10 to the minus 7. So I wonder if Shulkinoff would be excited if he were alive if this would obey his theory. And it turns out the answer is no. Well, it doesn't obey his theory, and maybe he'll be rolling over in his grave because something completely different happens when you get to atomic scale conductors, which I'll discuss in a moment. Well, I'll discuss it first, I guess. So when you make conductors atomic scale, more specifically, when you make conductors the size of the quantum mechanical wavelength of an electron, then interesting things happen, just like in a single mode optical fiber or a single mode microwave waveguide. But here, they're electron waves. So what happens, to make a long story short, is that if you have a single mode electron waveguide, an analog of a single mode optical fiber, there's no resistance along the length of the waveguide, but there's resistance at the contacts, which is the resistance quantum at DC, which is h over e squared, which is 25 kilo ohms. Now, everyone in this community is all familiar with the characteristic impedance of free spaces, which is a typical ratio of the electric field to the magnetic field in a guided wave or in a free space, even light. So there's this inherent mismatch between atomic scale conductors and free space. And the story gets more interesting. This led to the field of nanoelectromagnetics, that is how do two-dimensional and one-dimensional electrons behave when they are coupled to waves. Well, the DC resistance is h over a squared, and what I showed and proposed many years ago was that what is the AC properties of a one-dimensional electronic wire. By the way, you can make a one-dimensional electronic wire with a carbon nanotube, so it's thin enough that at room temperature the electrons are really behaving as if they're in a single mode matter waveguide, just like a single mode optical fiber. So what happens is that it forms a transmission line that's got a different characteristic impedance and a different wave velocity than the classical transmission line. And the wave velocity is the Fermi velocity, and the characteristic impedance is the resistance quantum. So this is a quantum transmission line. So I predicted this, and George Hansen took this idea and ran with it to calculate rigorously the properties of one-dimensional antennas. He became an IEEE fellow based on that. He won the Shulkinoff Prize based on that, developing a more rigorous theory of one-dimensional antennas. Leal and Intel measured the inductive part of that impedance at microwave frequencies in the 2010s. And other groups had measured the capacitive part as well. And it's a very small capacitance, it's a very small inductance. So it gives rise to some very difficult measurement challenges. And we had a lot of discussion with Keysight over the years about how to develop new instrumentation to measure high impedance devices. Now, before you get your hopes up that this can be used in practical applications at room temperature, there's also resistive damping, because we live in the physical world, and that actually dominates the transmission line behavior. So you're over damped unless you're above about 200 gigahertz at room temperature. So if you're going to do a terahertz antenna, it may work with one-dimensional electrons, but if you're at microwave frequencies, it's going to look like a resistive antenna. That's a better slide. So we demonstrated a nano radio. It got a lot of press, but it was just nanotube was just a diode detector. It wasn't really a nano radio. The antenna is shown here. And there's been, I'll do this quicker, there's been quite a bit of progress since then to make very small radios, but to my knowledge, nobody's built a radio that fits into a single cell. The smallest is about 300 by 300 microns. So it should be possible using conventional technology to scale this down to, let's say, 100 microns. But if you get down to the 1 micron scale, I think you're going to have to do something more sophisticated or live with an extremely compromised antenna. So that's still to be done. And how would you measure the antenna performance? How do you measure the impedance of these atomic scale devices? How do you measure the radiation pattern of a nano antenna? So there's been a lot of work also at Lille on measurement techniques. And one of the new techniques that became very interesting to the community was to take an AFM technology, and instead of measuring the tip force between the tip and the sample as you scan the tip, just measure the microwave reflection off the end of the tip. And that gives you information about the local electric field distribution of the microwaves. And Keysight commercialized this. They bought an AFM company, they connected their VNA. This is their generation 1. We and others in the community pushed them to have it work in liquid for life sciences applications. This is their generation 2. And Peter Siegel wrote a really nice review article in IEEE Journal of Microwaves in 2021 if you want to dive deeper into the history and details of that subject. In the interest of time, I will go to the interesting part of this discussion. Let's continue on. So the question then is, so in Peter Siegel's article, he talks about it, and there was a whole workshop on it Monday, where you can probe microwave properties of nano-electronic systems. But what I think is an interesting frontier is probing living systems. So can you probe living systems with microwaves? And here's a picture of a cell. This is the nucleus. These stringy things are mitochondria. It turns out each mitochondria has its own DNA, so that's an interesting property of cells. So can you probe that? And with microwaves instead of light. And what's more interesting is, can you probe it while it's alive? So the Nobel Prize in Chemistry in 2014 was given for super resolution optical microscopy. And the killer app for that on the Nobel Prize website was imaging the internal structure of mitochondria. That's what's shown in the right-hand side. And traditional confocal scanning microscopy is you scan a laser across a system and measure the transmitted or emitted light or the fluorescent light. So it's a single pixel scanning. And you're limited by the wavelength of light. And with special techniques, you can get below the wavelength of light. That's why I got the Nobel Prize. However, most of the work in that field is done on fixed cells because the laser is extremely intense to get that high spatial resolution. So only recently has what's called live cell imaging become possible with super resolution microscopy, and that's a very important development, but it wasn't easy, and it's still not easy because cells are fragile to the intense laser pulse. So can you do the same thing with microwaves? Can you do scanning microwave microscopy of living systems? So in a few minutes, I can describe the state of the art of that field and where it could be going. And the state of the art is that, yes, you can take living systems, measure them with an AFM, just like you could, there have been a lot of work doing AFM of cells and subcellular organelles. And what we've shown and others have shown is you can take mitochondria out of the cell, keep it alive. So these are mitochondria that are taken out of the cell, and they're kept alive for about an hour in this buffer. And there's there's a red stain here that shows they're alive. So this is live cell imaging with microwaves. But you really just see a blob. You don't see inside because you're just scanning over the surface. And that also can be done with cells. And together with Camille, we also developed ways to calibrate the impedance between a sharp metal tip and the ground plane using basically an open short load calibration, which was developed by MC2 Technologies and commercialized. They have a booth here. It's not really open short load, it's 3 capacitance standards, C1, C2, C3. And on the bottom right, if you can see my mouse, we made our own capacitance standards based on that technology. And then there's an image of a cell that's a scanning microwave microscope image of a cell that's alive. And on the slide here, where my pointer is, you can see the calibration discs, and you can see the cells that are fluorescently labeled. That particular fluorophore is proof of life. So this works, but you can't really see what's going on in the cell because you're scanning over the surface. And you can impale the cell with the tip, and then you get different impedance between the tip and the ground plane at microwave frequencies, which is all calibrated, but it's also still not a general purpose imaging technology. So I think the next step in this field is to stop measuring the capacitance. Let me go back 2 slides. Okay, the way that scanning microwave microscopy works is that there's a sharp metal tip and then there's a ground plane. And there's some capacitance between that tip and the ground plane, which is maybe 10 attofarads. And at microwave frequencies, it's possible to measure that capacitance as you scan the tip, and you get some spatial imaging, you get some contrast. So the question is, what does that mean physically? Well, there's fringe fields here, so you're really averaging out the dielectric constant of everything between the tip and the ground plane. That's about not the diameter of the tip, but it's spread out by the height of the tip above the ground plane. So what we really need to do is to create a better tip, for example, coaxial tip, and then not just look at one frequency capacitance, but look at the capacitance at many frequencies, or the impedance at many frequencies. And that's the frequency domain version. The time domain version is radar. So I think the next step in this field is to make a nano-radar. And then you could scan the coaxial probe, and you wouldn't have to impale the cell, and you could do reflection off of the components of the cell. It would be a little nano antenna. And this could be done broadband, whereas traditional radar is limited because of interference with other communication technologies. So we've started work in that direction, and I think that's a very exciting future direction to use waves to probe the nano world. So that's waves for the nano world. Now what about waves for the macro world? And this is going in completely the other direction. So I think one of the biggest applications is going to be in aviation. And this is a quick slide I put together of the history of aviation. In 1900, we had the first human-powered flight. I'm not going to say the Wright brothers did it because I know France played a big role as well. But then in 1950, we had the jet age. And then in 2000, we have the unmanned aerial vehicles age. And that is just beginning to be broadly deployed and is really transforming aviation. And maybe in 2050, we'll have Jetsons. Instead of self-driving cars, we'll have self-flying airplanes. And this is a schematic. And waves are going to be used to control and measure all of these. And this is a very important application of waves and microwaves in this revolution in aviation. So where are we and where are we going? Well, the number, this is for USA, but it's similar, I'm sure, in Europe. The number of unmanned registered pilots in the USA vastly exceeds the number of registered manned pilots, even a few years ago. So pilot meaning, drone pilot. And not all of them register. So the number of unmanned aerial vehicles is exploding. But they're all limited to line of sight because of safety considerations. So this is where I think microwaves will and are going to and are playing a very important role in sensing and controlling air traffic with unmanned aerial vehicles. And this is a very big space that academia, industry, and government are playing a big role in. And the limit is the government, And the government's limit is the safety, which comes in the safety's limit is the technology. So we need microwave technology to enable spacing, safe spacing between all these, this new generation of aviation, which even now in its infancy, the number dwarfs the number of manned aircraft. And it's very limited now in scope, but eventually it won't be. So we've done some demonstration proof of concepts in my lab. I was at a conference in Reunion Island, which is a French country, territory down off the coast of South Africa. And if you drill a hole, my parents used to tell me, if you drill a hole in the ground, you're going to end up in China. That's what parents in America tell their children, because you go to the other side of the world. So if you drill a hole in the ground in the US, you end up in the middle of the Indian Ocean. But this is as far as you can go from where I live in the world. And we were able to demonstrate the control of a drone. There was a pilot in Reunion, the drone in Irvine, to create this remote control link. And these are the pilots. It was a student group in Reunion, and these are the students in my university that developed the software, and the coding was done over the internet. And we were able to demonstrate remote control of a micro drone from around the world. So this really is a proof that you can do long-range control, but the question is, how do you do the coordination and safety? So if you look at the history of UAVs, this is Howard Hughes, and he actually had a remote control model of his Spruce Goose, which is the largest airplane that ever flew. It only flew once, but while he was testing it, he had a remote control version of it. Here he is testing it. Of course, in the 2000s, we have military large drones that cost hundreds of millions of dollars-ish. But now we have micro drones that are very, very inexpensive. So the field is changing fast, and there needs to be a way to coordinate all the different aircraft that have no pilot in the aircraft, and to integrate unmanned and manned systems. So right now, there's two possible solutions to that using waves. One is direct broadcast, and the other is cloud connectivity. And it's not even really communication yet, it's just transponder, it's a beacon where the unmanned vehicle broadcasts its, or transmits its location. There's no control yet, this is just location. And as of now, all drones, almost all in the US and the European Union, are required to have a direct RF broadcast, but it's Bluetooth and it's, or Wi-Fi, so it's not that long range. It's maybe a kilometer of range, best case. So that's not good for long term. So long term, the appropriate method is to have some sort of cloud connectivity and software behind it controlling it. And so many companies are participating in developing this back-end cloud-based command and control, and the name for that is unmanned traffic management. Google has developed with Wing and partners here in Europe a software suite, which is open source and available on GitHub, to take a first step at that. And they did a demo in 2018 with multiple different UAV sizes and multiple different companies. My lab, we worked on very, very tiny 4G connected UAVs. So there's a lot of work on 4G connected UAVs, but most of them are pretty big. So that's another research area where this community can contribute. And there's no reason you can't have small transponders on small drones for 4G connectivity, and I don't see any companies doing that. So this is a great topic for future commercialization and technology development. What does exist for long-range command and control in the commercial sector is, and there are companies that have developed this, there will be a remote pilot that connects over the internet to a local pilot. The local pilot has a transmitter that connects via radio waves to the local drone that's kept within line of sight. So this is not really a good long-term scalable strategy. A better one is to have the connection through the cloud, which is shown in this cartoon. And we've actually developed, in my group, open source cloud control stations. So not just have the pilot on the ground and the internet is just a pipe. We actually have the control station in the cloud, and anyone can log onto that website from anywhere in the world. Talk to me, I'll give you the password. And then you can control one or a swarm of drones with the cloud, and all you need is a web browser. And there's a couple startups also. We did that at the university, so I would say it's alpha testing, but there's one or two startups that are working on this also. And again, the issue is the integration of the unmanned and the manned aircraft in a safe system. So we can do a lot of technology developments, but they really need to be demonstrated in the physical world. And then the other possible application of drones and waves is not waves to control drones, or multiple drones, but drones to probe the physical world. And again, we've done some work on this, and there's two topics that drones can be useful for in microwaves to probe the physical world. One is propagation models. So if you want to know the propagation from a base station to a receiver, the current model is a variation of the Hata-Okamura model, which is based on Okamura's 1968 ground vehicle propagation experiments. I like it, it's empirical. And it's evolved since then, but these are all ground-based measurement campaigns, and the model is for ground-based receivers. So Qualcomm in 2017 did a little bit of work on this for airborne receivers, but they didn't focus on the propagation losses, they focused on the base station switching times, which is also important. So I think it's important to develop propagation models in this new regime where it's not you have a transmitter, you have a receiver, but you're not looking at the ground base, you're looking at ground to drone. And I did a little bit of work on this by mapping out the signal from a base station and showed a couple different interesting properties with drone to ground propagation. One is ballistic propagation, where the waves propagate directly from the receiver to the drone. Another is interference, where you have two interfering points and the waves interfere constructively or destructively with the drone. And the other is diffusive propagation. If the drone is in the valley and there's lots of scattering sites, there's diffusive propagation. So I think this is an important unexplored area, is looking at propagation models of high altitude, ground to drone. Another one is, and drones can be used to probe that and to develop new models. And another one is the opposite, which is very close to the ground. So most of the Hata model is for receivers that are a few wavelengths above the ground, because the wavelength at 1 gigahertz is 30 centimeters. So you're usually 1 or 2 wavelengths above the ground. That's what the models are for. But another interesting model is to look at ground-based propagation. And this is another drone. It's a ground drone. And I don't know if they have these in France, but it's an unmanned ground vehicle that they have at UC Irvine. A couple other universities have this. And it brings you your coffee or your lunch. Now, this goes against Parisian tradition of going and sitting down in a cafe and enjoying your coffee, but America everybody's always going, so they don't want to stop and have lunch. They got to have their lunch brought to them by a ground-based drone. So, both of these are interesting topics to look at for propagation, and I'll just show you one interesting picture here in the interest of time. This is a picture of the setting sun and the lake. Now, if the lake were smooth, you would see an image of the sun, but the lake has ripples on it. So what you see is a line of light. I hope everyone can see that. Why? Well, it's an electromagnetics propagation problem. So the typical, crude model for propagation of microwaves, and the same thing applies for microwaves. It's called the plane Earth model, where you model the Earth as a perfect conductor. So if you have a transmitter, you're going to have the free loss directly from the transmitter to the receiver, and then there's going to be reflection off of the ground. So the transmitter, there's an image of it, because it's the method of images that you model the Earth as a perfect conductor. And that gives you 40 dB per decade of loss beyond some breakpoint. The empirical model has this 40 dB loss in there that's used in industry. That below that breakpoint, there's an empirical 20 dB, which is empirical. But Sarkar, who was the president of the IEEE Antenna Society, very smart man, looked at this picture in the microwave and thought very hard about it and showed that this two-ray model is actually wrong. The Earth is not a perfect conductor, and it's got a lot of scattering sites on it. And what that means is that if you have a transmitter in the Earth, which is an imperfect conductor with ripples that are of order the wavelength and size, then the image of the transmitter with the methods of images is no longer a point, it's a line source. And he predicted 30 dB per decade between these two breakpoints, which some of his empirical data showed. So using drones, you can probe all of these at different heights. And I'll show this slide as an example of how drones can be used to expand these propagation models. The HADA-COST model, if you put for 900 megahertz, is really for HRX over lambda around 10. It's the receiver height divided by the wavelength. And the transmitter height is typically 100 to, 10 to 100, the transmitter height divided by the wavelength. But drones operate in this other regime where the receiver height divided by the wavelength is 100. The HADA model does not apply there. We need more measurements and more theory there. And also, for the receiver height, very, very low, and the transmitter height, that's another unexplored area. So both of these are interesting areas for propagation that need to be explored and developed for applications in communication and control. One final application is using drones to measure antenna pattern, radiation pattern. So we were the first one to demonstrate this in 2016, and we took a patch antenna, a cloverleaf antenna, and a dipole antenna. The patch antenna is very directional, the dipole antenna is omnidirectional. It mapped out the signal strength by flying a drone around, and this is an interesting economical way of generating 3D data of radiation pattern in the field. This idea has taken off, and many groups now have started working on this in a more sophisticated method. This is a paper from 2019. I think it's in Spain to do antenna pattern mapping. And this could be done at RF. If you have the right receiver, it could be done at, microwaves. It could be done, if you have the right receiver, at RF, UHF, VHF, HF. I'll skip that and move on to the big application space, which is unmanned traffic management. So this is the future of aviation, is manned-unmanned integration. And the technology on the aircraft side is under heavy development for micro drones, people-sized drones, et cetera. Similar to self-driving cars, and there's heavy investment in this. And the US and the FAA and the European analog have developed standards. Oh, where'd that go? And then there's actually an ASTM standard now for unmanned air traffic control if they can all be 4G or cloud connected. So cloud connectivity is really the next frontier for unmanned aviation to solve the safety problem. And we need microwave receivers and transmitters for micro drones and other ones, and we need to know how the waves propagate in this new regime of propagation to make this revolution in aviation possible. So here's a timeline from 2019 until now. Like I said, I demonstrated the world's smallest 4G connected drone. I think it was 300 grams. And we and another couple other startups developed cloud-based control. We demonstrated in 2021 around the world control of a drone. EASA, that's the name of the FAA in Europe. In 2022, implemented the first law requiring remote ID transponders, but these are transmitters only. There's no cloud connectivity. And I'd like to make a plug here is that I don't personally think that the law should say that every drone should be connected to the cloud before it's allowed to fly. I actually put that comment into the rulemaking process at the FAA. They actually wanted it initially that if a drone is not cloud connected, it cannot take off. And I don't think that's a good idea for engineering reasons, and I don't think that's a good idea for democratic reasons. But for integration into the airspace, cloud connectivity is an obvious technological direction. So we demonstrated, I didn't have time, detect and avoid with the remote ID transponder 2024, but really urban air mobility is the next step, so that's coming. And what microwaves will allow is an integrated airspace system from toys to micro drones to human-sized drones to manned aviation. And waves will play a very important role in that structure, in that field. So I'd like to acknowledge my funding agencies and my collaborators. Especially I'd like to acknowledge the FACE Foundation, which is run by the French Embassy. And when I started working on this project with Lille, it was kind of like the end of Casablanca, where Humphrey Bogart said, "This is the beginning of a beautiful friendship." So Camille, it's been a beautiful friendship, and we really had a great beginning, and it's been really a pleasure to work with my colleagues in France on a lot of the topics that I had time to discuss here. So, and thank you for inviting me, and I'd be happy to take any questions.
Thank you, Peter, for this nice presentation. So we have time for a few questions, comments, or remarks.
Thank you very much for the very nice presentation. I had a curiosity about the nano antenna, the nano wire. Would you, because we saw the information about the input impedance, would you expect a radiation typical of wire antennas? And what about the radiation efficiency of the due to the losses of the wires? I don't know if you have any information about this.
Yes. So that's what I said. George Hansen spent a lot of his time calculating that, and we tried very hard to measure it. And there's two answers to that. In the terahertz, the efficiency can be reasonable, like, a few dB of loss along the arms of the antenna. But in the gigahertz, because you're overdamped, there's severe resistive loss along the arms of the antenna. The resistance per length at room temperature for a carbon nanotube is 6 kiloohms per micron. So if the antenna is, let's say 100 microns long, then you get 6 kiloohms times 100, so 600 kiloohms. So the efficiency, in that case, I calculated, the efficiency is about minus 90 dB. Minus 90 dB. Horrible, right? So that's what I was saying in the very beginning, is that if you're going to make nano radios, you have to be willing to compromise. I mean, that's a severe compromise. And it's like I said, it's not a long-range, high bit rate, efficient system. It's small. Now, don't run away like I did for a while, because the free space loss between GPS and the cell phone, that link loss budget is 180 dB. So it's possible for everyone in the world to have, for $1, a receiver that is ubiquitous with 180 dB link budget. So 90 dB of radiation efficiency, or of inefficiency, is bad, but it doesn't mean it can't work.
Thank you.
Thank you. Any other questions or comments? So if not, so let's thank the speaker again.
Thank you.
Okay, so now ready for the second speaker. So Bjorn Rommen, he received the master degree from Delft University of Technology. He's been working since then in the field of Earth observation at European Space Agency in the Research and Technology Center in the Netherlands. And he's currently a mission scientist for ESA Earth Explorer 7 biomass and Earth Explorer 10 Harmony missions. So he has been working on a wide range of microwave remote sensing applications, on microwave instruments, and leading research and developments to investigate wave interaction with Earth surfaces. He's also been involved in the Sentinel-1A and 1B pre-launch and post-launch activities. His research interests include electromagnetic theory, computational electromagnetics, and radar remote sensing. So, Bjorn, yes, the floor is yours for your presentation, which is here. Should be this one. Thank you.
Okay, thank you, Guido, for this for the introduction, and it's an honor to be here today, talk in front of you at EuRAD. Let me start the presentation. So, good morning, everyone. So we're going from Peter's presentation. We're going from nano to airspace. Now I try to bring you a bit higher to even to space. I'm going to talk to you today about synthetic aperture radar missions in development at ESA, overview, status, and application. So. It's going to be a wide field. I'm trying to cover a lot of things within the next hopefully, let's say 35 minutes. So please, sorry if it's not too much detail. I'm going to be here for the next 3 days. So if you need any more detail, then please approach me. Of course, since I'm talking about many missions, of course, many colleagues which I've acknowledged here as well. Let's say from all different projects I'm working with. So first, the overall Earth observation program and how, let's say, it has been divided, let's say, within ESA. Initially, we started basically with science missions, R&D missions for Earth observation, and it still exists. And you still see, let's say, that even after, let's say, more than 33 years, we still have, let's say, missions that are being, let's say, developed really for this Earth science pillar. As we are looking, let's say, for new biogeophysical parameters that we'd like to investigate and try to bring science and understanding, let's say, of the overall Earth system a bit further. That you see, let's say, in this first pillar. Then we have, since, let's say, the early 2000s, we started, let's say, with the European Union to work to bring this R&D missions into operations and to really come up, let's say, with an actual operational pillar for Earth observation. And I think up to date, this is probably, let's say, the most successful Earth observation operational system that is in there, let's say, globally, basically. So. And then last but not least, let's say, also, let's say, for meteorology, we are developing satellites for EUMETSAT, and these are, let's say, still in operation. So of course, you know all these, let's say, images that you see every day at the 8 o'clock news, at least in the Netherlands at 8 o'clock, to see, let's say, what type of weather is going to be, and especially these satellites have made sure, let's say, that actually our forecast skill has definitely improved by using satellites. So here, a bit, let's say, the ones that have been, the ones that I'm talking about, that have a synthetic capture radar on board. The first three ones, ERS-1, the Earth Remote Sensing Satellite number 1 and 2, that was, for ERS-1 was launched in 91 and was decommissioned in 2000, ERS-2 in 95, and actually we continued until 2011. And then NVSAT, that was launched in 2002 and was decommissioned in 2012. All these three missions had multiple instruments on board, of which one was a synthetic capture radar. So it was not really optimized, really, let's say, for SAR in general, because also optical instruments were basically on board as well. Then, since launch in 2014, Sentinel-1A, which is a C-band SAR instrument, it's basically only, let's say, dedicated for C-band SAR. It's called the C-SAR instrument on board. And Sentinel-1B, which we launched in 2016. And then you see all the planned missions, the upcoming missions that are still going to come, which is one in the science pillar. We have basically two missions: Biomass, Earth Explorer 7, and Harmony, the Harmony mission, Earth Explorer 10. I will go into detail in this one, let's say, later during the presentation. And then then of course Sentinel-1C and 1D, which are nearly identical to the first two units that we've been, and those will be the first one. Those will launch as well, let's say, very soon. And then the L-band missions are called Roselle. They will come as well later. And then later on, let's say, talking about, let's say, 2032 and beyond, the Sentinel-1 next generation will be flown, hopefully. So overall, let's say, within ESA, we have about 37 satellites in development and 17 satellites in operation. So it's quite significant. Okay, this is again, let's say, the overall picture, but I'm only showing you the synthetic capture radars. Here you can see, let's say, the unique vantage point that we have, let's say, with SAR. So we have to imagine that we're flying, let's say, at roughly, let's say, 700 kilometer altitude. We're going with a speed of roughly, let's say, 7 kilometers a second, and we are scanning the Earth, let's say, from this distance. And that's what you see basically here with Sentinel-1, who's operating, let's say, and taking a 250 kilometer instantaneous, let's say, measurement, let's say, of the Earth's surface, which is then being used for different applications like earthquake monitoring, urban monitoring, land subsidence. And we'll go into detail as well of this. So what you see here as well, let's say that, of course, in the range direction, a synthetic aperture radar works like any other radar. So it's like you use the bandwidth, you use a chirp, and then basically you get your range resolution. In the along track, we use, let's say, the Doppler history of the targets, let's say, to focus the image and get, let's say, proper azimuth resolution, which is typically then around, let's say, half of the antenna wavelength in azimuth. So here you see the type of nice images you can make. Of course, these are, but they're all, of course, based, let's say, on the microwaves that we are emitting. So here you see, let's say, on the left, you see the first image, let's say, that we took with ERS-1. This is a picture of the Netherlands, and on the right, let's say, with Sentinel-1. Many years later. So you see now we have overall, let's say, 33 years of consistent archive at C-band, and the C-band for us, let's say, is around 5.4 gigahertz. And you see really here that this is still consistent. Now, of course, we can play a bit more. In the beginning, it was only VV-pol, so vertical receive, vertical transmit, vertical receive. And nowadays we have a dual-pol system, so we can nicely color the image. And one step further, because of the increased, let's say, temporal resolution that we now can offer, let's say, with these systems, we can actually do, let's say, for example, let's say, crop monitoring at field scale in the Netherlands. And here you see an example of 800,000 fields in the Netherlands. And I'm always surprised by seeing this, because people always say Netherlands is a very densely populated country. But if you look at this only at the agricultural fields, you basically see the Netherlands. So there's at least plenty of room there. And I think about 60% of the Netherlands is being used by agriculture. So then one step further on INSAR, SAR interferometry. So one thing is, of course, to make very nice images, where, of course, for which you can use, let's say, the radar reflection coefficient, which we call the normalized radar cross-section, to make nice images. You can use the polarimetry, and you can make beautiful things. You can also use this, let's say, for classification, for a better understanding of what's happening at the Earth's surface. But one important thing about to use in SAR is actually to do interferometry. And for this, of course, you need to have a very stable orbit, because in most cases we do this by multi-pass, which means that you come, let's say, on Monday you come over a specific area, you have exactly the same orbit. Next time you fly over again, exactly with the same orbit, and you're able, let's say, to do with a very, very intricate processing, you'll be able to do interferometry. And by doing this, you can actually get, let's say, things like you can look at the overall subsidence, you can look at Earth deformation processes, but also, let's say, looking at subsidence even in urban areas. So now going to the overall Copernicus SAR context. So I've talked to you already about, let's say, the missions that are there. So the current generation of Sentinels, Sentinel-1A and B, and Sentinel, which are both, let's say, flying. Sentinel-1B, we had an anomaly with it, let's say, end of December 21, and actually since 2 weeks ago, we decommissioned the satellite, so brought it to a lower orbit, so it would actually naturally decay there within a number of years. Sentinel-1C and D will be launched in the course of the next year. The next generation Sentinel, of course, I mentioned, say, Sentinel, it will be 32, and then, of course, talking about Roselle. But what I will talk first about here is the C-band systems of Sentinel-1. So here you see a nice artist's impression of the satellite itself. So Sentinel-1 a bit in a nutshell. So it's a constellation of two identical SAR satellites. So they're flying, let's say, if you look at the Earth, we're looking, let's say, we're flying all our static capture radars in roughly, let's say, 98 degrees inclination with respect, let's say, to the equator. And by doing so, we're in a fixed plane. The Earth rotates underneath us, and by doing this, say, we're able, let's say, to get a full global mapping of the planet, let's say, within a number of days. Now, if you have now we have two satellites, so where to put them? Then the idea what we did for Sentinel-1 is to put them, let's say, within, let's say, 180-degree phased within this plane. So one is flying here, the Earth is in the middle, and the other one is flying here. So, but you will see that it will always be in this plane. And by this, you create, let's say, an actual 6-day, instead of, let's say, when you have a 12-day actual repeat, exact repeat for interferometry. By doing this, and you have a full global coverage within this 12 days with one satellite. If you do it like this, you actually get 6 days with the two satellites. Overall, they were built, let's say, for 7.25 years lifetime, and the 0.25 is because we need about 3 months to actually commission the system. So we have 7 years of operations, and we have consumables for 12 years and even more if you wanted to. As that center frequency I already mentioned, it's a dual pole system. The overall incidence angle is ranging between 20 to 45 degrees. Radiometric accuracy of 1 dB 3 sigma, so quite high, even better than our previous systems that we've been flying, and with a noise-given sigma naught of minus 22 dB, which is actually the noise floor in the image. And what is very important is full, free, and open data. So all the missions that you've been seeing, let's say, it's of course not the highest resolution of SAR data that you can get, but the thing is, it is global, it's of homogeneous quality worldwide, and it's fully available and for free available to the community. Then talking about the imaging modes, we're looking at, let's say, the main operating mode is what we call TOPS. Terrain observation by progressive scan, so which has, let's say, slight, let's say, scanning in azimuth, about ±1 degree, to make sure that the radiometry is constant during the scan SAR, accessing, let's say, the different subswath that you see here on the left bottom. So we have 3 subswaths in the IW mode. Then, of course, we have all strip map that we use very limited, let's say, but of course we have also the wave mode, which we use, let's say, over the ocean, which is, let's say, kind of what you see here. We call it the leapfrog mode. Is scanning, let's say, every roughly 100 kilometer, a different, let's say, vignette on the ocean, roughly 20 by 20 kilometer, 5 by 5 meter resolution, and as well the extended wide swath, which will give us a 400 kilometer of access instantaneously. So Sentinel-1C is getting ready for launch. We're looking now, we're soon starting now commissioning preparation. Have actually already started, and soon going to be shipped to French Guiana. So here you see, let's say, the latest pictures of the satellite itself. The SAR antenna itself is about 12.3 meter by 0.8 meter roughly. It's consisting out of 2 wings, 5 panels in total. So you see here on top of the on top, okay, you don't see it, of course, but it's on the top of the satellite, but on top you've got basically the two panels, and then 2 tiles, sorry, and then you have on the both sides, let's say, you've got this folded, let's say, two panels on each side, which so basically you get a 3-3 to 3-3 configuration for the tiles. So in total we have 14 tiles each, with 20 H and 20 V slotted waveguide arrays. So that you see here, you see a magnification of one of the tiles. So in total we have 280 H and 280 V polarized TR modules, which are each of 15 watts each. So you get roughly around slightly above around 4.2 kilowatts total. And for the waveguide arrays are built in the metallized CFRP. Okay, then an overall, say, comparison of our C-band systems since we first launched the first one in '91. So, and if we're then looking, let's say, at the increase over time with respect to what we've been able to do in the main operational mode, you can see directly, let's say, from this table that we've gone up, let's say, in the excess of the swath, instantaneous swath, coming up from 80 to 100 kilometer to 250 kilometer, and trying, in this case, let's say, maintaining the resolution. Although, let's say, slightly different, you see it's 5 by 20 and 20 by 5. But if you then look, let's say, at what we call, if you make a performance indicator, then you see basically that it has increased, let's say, by a factor of 4. And of course, you all know, let's say, it's not so easy that you are still ruled by the rules of physics. So to go, let's say, in a huge step forward here takes time, and the next generation will take into account some additional processing schemes to try to go beyond what we currently have. For example, there we are targeting a 5 by 5 meter resolution, and then having an excess of, let's say, 400 kilometer. So in that case, let's say this performance indicator would even be driven up even further. So the important thing is going from R&D, and because I told you to say this was the science pillar, we're going now in operations for the mission, say, that we're doing together with the European Union, is looking at the overall coverage, because then you would like to have, let's say, kind of a global coverage. What we got, let's say, with NVSAT and with typically ERS, we're looking at 80 kilometer swaths. You see here the ascending, descending swaths, which happen within the 5 days. You see, let's say, the coverage within this basically Central Europe here. You see, looks fine, but okay, it's not too impressive. Now, if we go then to 250 kilometer from with a single satellite of Sentinel-1, then you see indeed that this has improved significantly. If you then move up, let's say, to the full constellation, which is operated every time, especially over Europe, then you get, let's say, an enormous, a great coverage. That also explains why, for example, now we can track agricultural processes much better, because there you need something, let's say, ideally daily, but within a couple of days, an image would be great there. And looking at the overall timeline here, Sentinel, the first generation, is so let's say we have Sentinel-1A still in operation. Beyond, to say, we've now gone beyond, let's say, 10 years in space. So it's definitely something to celebrate, and we hope it can continue a bit further. As I mentioned, the constellation, we had a failure, let's say, anomaly end of 21 on the 1B, which was only operated for just over 5 years. So it was not meeting it, let's say, 7 years lifetime, unfortunately, due to an anomaly of the antenna power supply system. And we now hopefully have, let's say, the Sentinel-1C coming in operations by the end of the year. So we'll have the constellation back in operations again. So here you see the difference, what you have, let's say, if you operate, for example, with one system or actually with two systems. So if we talk about a constellation, we basically we have a very dense coverage, let's say, of Europe. And basically every time the satellites are flying over Europe, they will, and over the coastal waters, they will image it. And then you see as well that you have, actually with the two satellites, you have every 12 days, you got at least a coverage globally. And with a single satellite, you see on the right, we are not able to meet this, of course, because of the operational duty cycle in the orbit, let's say, which is for Sentinel-1 roughly around 25 minutes per orbit. I told you, let's say, it's about, let's say, flying 700 kilometers, so it's 100 minutes to make a full rotation in this plane. And then we basically will not be able, let's say, to get this global coverage. It's used in a lot of, let's say, Copernicus services. So you see a couple of examples: emergency management service, also for marine environment. So looking at, let's say, sea ice, ice replication, also, let's say, ocean surface wind factors and swell properties. Land monitoring. I show you some examples on agriculture already, but also looking at the ice sheets and glaciers in Greenland and the Antarctic. Climate change service. So again, the sea ice and the security service for oil spill detection, and as well, let's say, for maritime surveillance. Looking at this, so we can think about ship detection, etc. Vessel location, size, and velocity. Then we go on supporting a rapid, let's say, response to crisis. Here you see an example of, let's say, I mentioned about interferometry, what you will be able to get. This is an example of using INSAR, following an earthquake in Morocco. I think it was a 6.9 magnitude earthquake in September 23. And the Sentinel-1 acquisition was done slightly just before and after the event, so pre-seismic and post-seismic event. And you see basically what you can get is to get, let's say, from these interferometric fringes, we can then deduce, let's say, the actual ground deformations. And this will actually help to to understand that the actual damage has been done. One step further, if you then use, let's say, an overall timeline and you combine all the interferometric measurements you have over time, you'll be able to follow, let's say, specific point targets on the ground over a long duration of time. And here you see, let's say, from the European Ground Motion Service, you see what type of, let's say, products you will be able to provide here. So you see for each of every of these points, you can actually track then the actual subsidence history over time in east-west and vertical. So one thing to keep in mind is what we can do basically from, I mentioned already, let's say flying 700 kilometers altitude, 7 kilometers a second, and we're able, let's say, to position, let's say, each of these point targets within like one cube volume on the ground, and we're able to track 1 millimeter accuracy per year over time. So this is quite impressive, I find. Then as well, going back to supporting rapid crisis, here we're looking at, say, Typhoon Hagibis from October 23, that we're actually trying to track with the SAR as well. And here you're looking at, let's say, 60 kilometer, let's say, eye of the hurricane. Okay, this is a typhoon, but it's comparable to Category 5. And on the right, you see for Hillary, let's say, in August 23, as well, they were actually able to track the system and is able, say, to give, let's say, a much higher resolution of, let's say, the core of the system and to understand what actually is coming towards, let's say, land. This is not yet an operational service, but we are trying to make this as well an operational service, given, let's say, the importance of this type of information for evacuation purposes, etc. Then we have a very, let's say, for mapping land cover globally. You can imagine, let's say, if you have a system that is operating, let's say, roughly 5 by 20 meter resolution, you will be able, let's say, to get using Sentinel-1, and in this case as well, let's say, Sentinel-2, which is the optical system, to combine this to get a very nice, let's say, global picture of the planet in terms of land cover. This is a freely open, let's say, available data set, which has a 10 by 10 meter posting globally, which will be able, let's say, to give you the exact, let's say, the land cover globally. And it's being updated as well. Let's say, I think the last update, I think, was in 21, but I think it's the most accurate, let's say, until now that is around. Then moving now to the Earth Science pillar, we're still in C-band. For the Harmony mission, this is Earth Explorer number 10. And we call this as well our ESA's dynamic surface mission. This is a kind of artist's impression of the system. And this is a passive SAR, so we're looking really here in this case about, let's say, a passive SAR that's operating together with Sentinel-1. So we've been talking about Sentinel-1. It's in a loose convoy with Sentinel-1D, which still has to be launched. Harmony will try to launch the system end of the decade. And this payload suite consists of, as I mentioned already, passive SAR, but also a multi-view thermal infrared instrument. I will not go in detail on the thermal infrared in this presentation, but just to give you an idea on the actual, what we're actually trying to measure with it. We've got two phases, which I think is important to mention. We've got one we call a cross-track interferometric phase, covering land applications like glaciers, permafrost, and volcanoes. And by doing this, I already mentioned, let's say, interferometry that we can do, let's say, by multi-pass. In the case, of course, when you've got two receivers close to each other, then you actually can do a single-pass interferogram. And this is actually what we try to do here with the mission. Then we have as well another mode, let's say, where we try to go, we call a stereo phase, and we're looking in both cases, the distance from Sentinel-1 is about 350 kilometers, sort of, let's say, 50 seconds in time. And one, let's say, flying, let's say, we call the stereo configuration, where we're actually moving, let's say, the systems, let's say, on either side of Sentinel-1. And there we can cover 3D surface deformation over time, and also ocean applications, surface motion, surface wind, sea surface temperature, and cloud motion. And the thing why we can do this is because of, and I will show this again, is that we can do, of course, multi-pass, let's say, in SAR, let's say, using the full antenna of the system. But if we use, let's say, only the single, let's say, for single pass for a long track interferometry, we can use the two ends of the wings to make a long track interferometry. And with this, actually, we can get instantaneous information about the currents on the ocean surface. So Harmony is really a multi-domain Earth system mission. So as I said, it's not an operational mission like within Copernicus, but it's really like trying to assess specific science questions. And what we're doing here is to look at the upper oceans, ocean-atmosphere interactions, land ice and sea ice, but as well tectonic strain and volcanic processes. Why we're doing so many of them? Because we know we can do them all well. This is what we know from all our, let's say, history, the heritage, let's say, at C-band. It would be pity to just pick one and fly a science mission without missing all these fantastic, great science that we could do with it, potentially. So we'll get, let's say, sub-kilometer scale motion vectors and topography changes associated with dynamic Earth system processes. So one is for air-sea interaction, tropical, extratropical cyclones, and ocean mesoscale and submesoscale processes. Glacier and ice sheet mass balance and glacier dynamics. And tectonic strain and factors associated to tectonic strain and topographic change at active volcanoes worldwide. So here you see again, let's say the pictogram I had earlier, let's say for the stereo phase. So there we have the slow, the differential INSAR, so multiple paths, let's say, combined to track deformation over time, but as well the Doppler surface motion vectors. And the second one is making use, as I mentioned, about this to, let's say, extend, let's say, of the antennas on both sides, so of the Harmony system. Directional roughness, so we get wind scatterometry, so we see, let's say, we get backscatter from multiple look angles, and with this, let's say, we can actually get, let's say, unambiguously retrieve wind speed and wind factor, the overall wind factor, basically. The SST is doing, of course, sea surface temperatures being done with the thermal infrared instrument, which also gives, let's say, cloud top motion vectors. Then talking about, let's say, some specific topic, let's say, from Harmony, is that we'll have, let's say, we're looking at the Earth-West strain, typically, let's say, with a single system. So with Sentinel 1, is, as I mentioned, is flying, let's say, in this 98 degrees inclination roughly, let's say, so typically almost north-south. And its line of sight is looking at the right. So, and it's basically the only sensitivity it has is in the range direction. So what you can measure there is that the east-west, you get sensitive to east-west motions, and by combining ascending and descending, you'll be able to get, let's say, as well, an understanding of the vertical deformation. So now, Harmony will be sensitive to all the components of this deformation because we have this several, let's say, as I mentioned, several look angles. So here we have looked at a typical, let's say, east-west oriented fault, typically Anatolia, in Turkey, as I shown in the previous slide. And now we're trying to reorient this slide, let's say, reorient this fault in the north-south. Then you can see that with GNSS, if you have GNSS receivers on the ground, of course you get points. But to connect these points to actual, let's say, a special, let's say, homogeneous field is quite difficult. With GNSS plus Sentinel-1, of course, you were very sensitive to the east-west fault, but not at all, let's say, to the north-south oriented one. Now, combine this with GNSS and Harmony, so Sentinel-1 plus the two Harmonies, then you get everything you want. And this is something that the community has been asking for since ever we've flown SAR, is that they don't have the sensitivity that they want, let's say, in the north-south direction. And by including the north-south as well, you get as well the overall 3D deformation. Then we're moving into this close, let's say, configuration, which is a single-pass cross-track interferometer. And there we're looking at, say, glaciers, permafrost, icebergs, and volcanoes. So talking a bit about the antennas, the overall antenna subsystem. So as I mentioned, we are working basically with three different phase centers. So one phase center is the two tiles, let's say, in the middle, and each of the wing ends are separate phase centers as well. And this is of course used for ATI. The overall baseline is about 10.5 meters between the ATI panels, basically. Total length of this antenna is 13 meters, and the design is fully compatible with the first generation of Sentinel-1. Something about the Harmony antenna tile. We're now looking basically at pre-developments. We just started, let's say, the phase B2, so we are, the critical design review is going to be held, let's say, only in 27 and launched in 29. But this is already what we can show today, the architecture of the SAR antenna subsystem tile. And this one has been defined consisting of a radiating front end, 4 radiating boards that you see here on the left, 1 tile beamforming network, 2 receive module units for each polarization, 4 power supply units, and a harness, of course. So how many in brief? Overall, let's say, so we're trying to get this order of kilometer scale on SST cloud top motion, directional roughness, directional Doppler, everything over the ocean is that typically in that type of order. Nice thing about C-band is it's typically all weather, so we can also look at, say, at hurricanes, and looking at those extremes, including polar lows and hurricanes, as I mentioned. 3D repeat pass INSAR, which is used, let's say, for the global strain, and dense DSM time series. This is something that you can do with this XTI configuration. We actually can build a single, let's say, digital surface model every time you fly over, let's say, in this XTI configuration. And then basically by combining several of these paths, we can actually do DSM differences. So we can really look at the difference between the DSMs that we got. And this is a very powerful technique and very easy to do, because basically what you're doing is just subtracting one height to another height, and you can ignore everything, all the process that has been done before. Then going back to the Copernicus SAR context again, Sentinel-1 next generation. So we're still at C-band here. Planned for operation from 2032 onwards, as I mentioned. And we're looking here at the overall performance requirements between what we're trying to achieve with the next generation with respect to the first generation. So Sentinel-A, 1A to D, and the next generation. So what we try to achieve is that we don't any longer have a North Pole gap. Mentioned, say, we're flying 98 degrees inclination, so we have a little gap, let's say, at the North Pole, also at the South Pole, but in this case we are more interested, let's say, to close the North Pole gap because of all the sea ice, for the sea ice charting. And this we try to close. Revisit globally, let's say, is more or less the same. We try to extend a bit, let's say, incidence angle range and the swath width, but as well, let's say, the resolution. Going to roughly, it's a 100 square meter resolution for interferometric wide swath. For Sentinel-1 next generation, try to achieve 25 square meters. And by that also including, let's say, the actual sensitivity of the system. And the actual duty cycle, operational duty cycle of the orbit, instead of 25 minutes per orbit of, let's say, operations, we try to bring up the system to about 43%, which is for 100 minutes orbit. As I mentioned before, it's a very easy calculation. You come to 43 minutes per orbit, which you can actually increase to 53 in some cases. Then going to the L-band one. So this is the L-band system for within the L-band SAR within the Copernicus. For Arctic and cryosphere monitoring, land and emergency mapping, and ground motion, soil moisture. Here you see again an artist impression of the system. This is a constellation of 2 satellites, very similar in terms of, let's say, completely different in terms of architecture, but in terms of the way we're going to use the system, it's very similar to Sentinel-1, because we're actually going to fly the system together with Sentinel-1 in the same orbit. And with this, of course, we're able to get, let's say, both L and C band globally and completely correlated. So we have here a coverage of, okay, as I mentioned already, let's say, so 6 days for the global land, 3 days over Europe, 1 day over the Arctic. And we're now currently in phase C. CDR is planned, let's say, kickoff in March 25, and we hope to have the first, let's say, system being launched, let's say, in 28, with the next one following a couple of years later. The impressive thing, of course, about L-band, we're moving, let's say, down from 5 gigahertz. Now we're looking at 1.2 gigahertz, roughly. Of course, everything scales with the wavelength. We're looking at the 40 square meter, let's say, overall aperture. I'll come to this in a bit more detail later. So again, here the type of services that are being, where Roselle will contribute to, apart from extending, let's say, the ones that we do already with Sentinel-1 and the enormous synergy we already have. So in interest of time, I'll move up this one. So maybe it's already, let's say, same orbit configuration. We do overlap with the Roselle interferometric wide swath. We do overlap very nicely, you see here, the actual interferometric wide swath of Sentinel-1. So basically then you really have the C and L band consistently. Depending on where we actually put it, let's say in Sentinel-1, we can then go down to a couple of minutes baseline, temporal baseline. And this is important, let's say, for the sea ice, where you would like to have, let's say, sea ice is drifting, and you would like to have, let's say, exposed much in time, let's say, to make sure that the images are fully correlated. Okay, so I think I can skip this one. Let's talk about the interferometric wide swath mode. And the important thing here, I think, intriguing thing is, of course, at L-band we're getting more and more sensitive to the ionosphere. So what we've done here is to have, let's say, an additional, let's say, auxiliary, let's say, band, let's say, part in the main band, still within the allocated frequency band at L-band, split band transmission to really enhance the ionospheric correction process. knowing that, of course, the ionosphere is a dispersive medium. Then looking at the overall SAR instrument itself. So we're looking at an 11 by 3.6 meter overall antenna. So it's quite a big surface. Here you're looking at the antenna consists of about 5 azimuth and 12 subarrays in elevation. So overall looking at 60 phase centers. And each of these phase centers fed by an individual dual pole TR module of 150 watt peak. So the overall radiated peak power of the system is 9 kilowatts. So we're going up a factor, almost a factor of 2 with respect to Sentinel 1 for this system. Each subarray consists of 2 by 12 radiating elements. You see it over there. This is the picture that you see there of the subarray. This is about to say, okay, between my hands, basically, this is what overall the length will be, let's say, of the subarray. So this is enormous size of everything what we're building, and what we have to launch, of course, because of course then we have to stow it and make sure it deploys properly, let's say, in space. What we do as well, let's say, is that we call it scan on receive in elevation. By doing this, we can get, let's say, additional, let's say, improve the overall radiometry. And the overall sensitivity. So by having, let's say, 3 adjacent elevation channels combined, both V and H, and then digitize, you can resolve, say, 4 digital channels that you can then use together to form a scan and receive beams. And that you see here. So basically, the transmit beam will still cover the full swath, but then by scanning the pulse, let's say, the echo, let's say, on receive, you'll be able, let's say, to get a better, let's say, sensitivity. On top of it, we have 5 digital channels in azimuth. We call it a multi-aperture processing scheme, which then can be used to reduce, let's say, the PRF or to work on the resolution, let's say, in azimuth, and whilst still maintaining or, let's say, fighting, let's say, the azimuth ambiguities. It comes, of course, with a cost because, of course, all these five azimuth channels have to be downlinked to the Earth then. Highlight for L-band, let's say, ground motion. You see here difference between C and L-band. What you're going to get, of course, you get slow deformation thanks to C-band. We got a long history, as I told you, over 30 years. But of course, in vegetated areas, C-band will not do so great. And this is what you see here. What you see, the L-band, you're much less sensitive, let's say, to decorrelation within vegetated areas. Same for land cover mapping. You get, let's say, improved flooding sensitivity, in especially vegetated terrains again. And this you see a nice example here between the C-band Sentinel 1 and the ALOS system, which is flown by the Japanese. CIs is very obvious. You really see, let's say, the complementary nature of an L-band image you see on the left and a C-band on the other hand. So you get really, let's say, it's directly clear, let's say, that you're sensitive to different, let's say, wave interaction, let's say, processes taking place and scattering mechanisms taking place in the CIs. Then we're moving to biomass. This is, again, let's say, Earth Explorer 7 mission. This one we're going to launch it very soon. And its main mission summary is really to take stock of the biomass in the world's forest, and especially, let's say, the tropical forests, which are let's say, the carbon stock is not known very well. We're looking at above ground biomass, typically it's like 200 meter resolution, upper canopy height, similar, let's say, resolution, and here we try to have a map every roughly 9 months during the mission. So you see how the systems will be working. Then we have the same for the secondary objectives as well. There we want to look at, say, since it's the first P-band SAR we have in space, and here the P-band, let's say, is of course UHF frequency, but the center frequency of 435 megahertz, so roughly, let's say, 69 centimeter wavelength. We're looking at, let's say, and because of this very large wavelength, we're able, let's say, to penetrate much better, let's say, in dry, let's say, arid areas, up to, let's say, 5 meter dry sand penetration, maybe even beyond. The same for topography under dense vegetation. Of course, with other systems, we're not able, let's say, to penetrate down to the forest floor. And by using this system as well, use the software interferometry, we'll be able, let's say, to get actually a digital terrain model under the actual vegetation in the forest, and measurement of glaciers and ice sheet velocities, as I mentioned already. So, what is the important thing here? It's a fully polarimetric system. High sensitivity, it's got a much higher sensitivity to biomass compared to all the other wavelengths. High temporal coherence over repeat passes, because of course you have a longer wavelength, you're much more, let's say, resilient for, let's say, decorrelation, temporal decorrelation. But on the other hand, we're going again lower. As I told you already, from L-band, C-band to L-band, we're getting much more sensitive to ionospheric distortions. Now we're going down from L-band to P-band, even a factor 4 lower. Of course, if the ionospheric, let's say, propagation is getting is going quadratic, so we're very highly susceptible to ionospheric distortions. We have a large wavelength. We've got a large antenna diameter. We got here a deployable reflector, 12 meter, actually 12.5 meter, but 12 meter projected. We have a focal length, I think, of roughly, let's say, around 7 meters. So it means that we are required to rely on a dedicated antenna pattern characterization in orbit, because we have no system, we have no way to actually test this on the ground, let's say, end to end. For this we have a dedicated development, which is called the biomass calibration transponder, which is positioned, let's say, in the North Sea, Australia, close to Perth. To meet the level 2 performance, the system must comply to high accuracy, of course, polarimetric, radiometric requirements, and the quad pole requires acquisition of the scattering coefficient in all the combinations, of course, which we then use for the retrieval schemes for all these applications I mentioned. We have 2 mission phases employing multi-pass interferometry. One is we call it tomographic phase, so this will be the first time we're going to fly, let's say, a mission that is actually focused on trying to do SAR tomography. I'll come in detail a bit later on this. And we have an informatic phase that will continue beyond the mission later. Okay, so here you see the actual observation capability where we have typically what you see with SAR. We can have, say, as I mentioned earlier, just looking at the intensity, we have a polarimetric system, so we can do SAR polarimetry. We can make beautiful colored images of the planet, and we can do this consistently. But the important thing becomes when you really put in, let's say, using a baseline, in this case a 3-day baseline, for doing SAR interferometry, for which we can then actually get sensitive, let's say, to the height here, because we use, let's say, special baseline to explore this. Then on top of this, we could do, let's say, SAR tomography, which we increase, let's say, the special baselines, in this case to 7, for which we then get, let's say, access, let's say, to multiple layers within the vegetation. And by doing this, you will be able to get, let's say, much better accuracy, let's say, of how to characterize certain forest biome to understand what type of forest you're looking at. And this will be the first time we're flying, let's say, tomography in an operational phase for a mission. So sun-synchronous orbit, 666 kilometer, 3-day repeat. You see here in the bottom, let's say, one day coverage. And it's actually then the 3 days using, let's say, the 44 orbits. You know, let's say, by then we haven't covered the planet at all because we only have a 50-kilometer swath. And we need to use a satellite role for swath access. So compared to the other SARs I just mentioned to you, this is a very, let's say, relatively simple, what we call strip map mode operations, 6 megahertz bandwidth. We need to roll to access, let's say, the other swaths. And after, let's say, each of these cycles, then we have to really switch, let's say, to cover, let's say, the intermediate points here that you see in this 3-day coverage. Okay, then one of my last slides. Here you see, let's say, the architecture of the system, of the instrument itself. You see the feed array, which consists out of 4 patches connected to the instrument as 2 doublets. And on the right, you see the actual interior of the instrument panel. The digital control unit, calibration distribution network, power amplifier, and receive amplifier. Digital control unit is providing is the heart of the instrument. It gives the instrument control and internal calibration functionality. The calibration and distribution network routes the transmit RF signals generated by the DCU, the digital control unit, to the power amplifier subsystem, and also routes the received radar ground echo back to the receive modules in the digital control unit. In addition, it also ensures the actual, let's say, the overall, let's say, internal calibration signals are being done well. The overall thing, the function of the power amplifier subsystem is to amplify the RF transmit chirp to a total peak power level of, let's say, 100 watts, 49.5 dBms. And the pulse is composed of 2 identical assemblies, as you can see here. One on the left and one on the right. One is doing one polarization, the other is doing the other polarization, so H and V polarization separately. And in principle, you have to use only 2 per polarization combined. There's one redundant that we can actually use in case one of them is not working to get back to, let's say, nominal functionality. And the receive amplifier subsystem is basically converted into the low noise amplifiers and make sure that for each polarization is able to route back to the calibration distribution network. So you see, if everything goes well now, you see a nice image a nice movie trying to explain what I just mentioned. So you see here the feed array, and basically the digital control unit. There, of course, a very generated chirp. So the chirp is being generated in the DCU, it's going down to the SSPAs, first, let's say, for horizontal polarization, going down, let's say, to the feed array, and then the same for V. So it's consistently, let's say, alternating H and V polarization at a very high PRF. Total, let's say, the system is about 3 kilohertz. And always have multiple traveling pulses at the same time. So here, of course, then the system signal is being transmitted to the ground, the echoes are being received, and then it comes back, let's say, to the receive amplifier subsystem, and it's going back, let's say, to the low noise amplification and back to the acquisition in the digital control unit. Okay, the biomass is getting ready for launch. We're very, very close, let's say, to the actual launch of the system. We're looking now at, let's say, April next year already, 25. So you see here, let's say, the instrument, let's say, the opening of the instrument panel on the left corner, let's say, left upper corner. You see the large deployable reflector, a mesh array done by, let's say, L3Harris in the US, in Florida. And the overall system that has been, let's say, was currently, let's say, current configuration. Right now it's in thermal vacuum, and it will come out with this, let's say, in the next weeks as well. So here you see the power amplifier subsystem with the SSPAs. This board is roughly, let's say, 1.5 meter by, okay, maybe 180 centimeters in total, just to give you some indication. This is my last slide. So, since the overall pioneering of the ERAS mission, I think ESA and Europe in general remain extremely committed to spaceborne stars for Earth observation. You can see for C-band, we've been doing all these missions, and we plan to say the next generation as well. For P-band, we have biomass, L-band, we have Roselle coming up as well. X-band, we have ESA third-party missions and the Copernicus contributed missions. So this is coming from more national programs. Upcoming launch, I mentioned December 24, launch of Sentinel-1C. April 25, launch of biomass, and September 25, launch of Sentinel-1D. So the future is now. Thank you.
Thank you very much, Bjorn. Very interesting presentation. So we have time for a few short questions before. Yes, please.
Thank you very much for this presentation. I wonder about the P-band antenna shape. What's your technique for doing calibration of such an antenna? Do you have some mechanical actuators on that, or I don't know how to keep it in?
You mean the antenna structure or the overall end-to-end calibration of the system?
No, but basically the umbrella structure.
Yes.
Which looks like some huge surface.
Yeah, it's
above the satellite. So I assume that will have some deformation of that time.
No, actually we hope it doesn't have any deformation. Luckily, I say this is the 100, as I mentioned, the 100 reflector that L3Harris is building. And there's a very, very fine mesh. And there's being, let's say, tightened, say there's a tightening system to make sure that the mesh is kept in shape. And of course, I say, but the mesh is much finer than actually what is needed, let's say, at P-band. And sometimes, let's say, P-band, when you were building, let's say, a UHF system, sometimes it's a blessing, sometimes it's a curse. It's a curse because we have to fly such a large reflector in space, which is quite difficult. But it's kind of a blessing in terms of, say, that in terms of toleration, you can accept a bit more than, for example, when you're operating, say, 5 centimeter. The overall, say, end-to-end calibration of the system is being done, let's say, on the ground. We have, and for your information, we have a accurate, say, antenna model that's been built, making sure the combination of the feed array and the reflector is done well. But of course, we have to. The only characterization that we can do is only once we actually fly the system.
So what I can expect, maybe the thermal dependency of the surface? I don't know which thermal span do you expect for such an operation? And also, the bore side orientation of this. Don't you expect that it can change over years of operation?
No, I think the good thing is space. I think once you launch and once things deploy, space actually quite, let's say, is quite a good environment in the end. Of course, the things decay over time, but things are very stable. So we don't expect, let's say, large deformation or changes over time. We have been looking at, let's say, things, for example, if you have, let's say, kind of space debris of some large small particles going through, let's say, your mesh, for example, or what the effect would be. But the mesh is configured in such a way that actually it will remain consistent. So, yeah.
Okay, thank you very much.
Okay, thank you.
Thank you. So, are there any questions? No. Okay, so let's thank again our speaker.
Okay.